Greetings. Today I'm going to be showing you a cool physics experiment that you can easily do in your own kitchen. And then I'm going to be talking a bit about how the science behind this experiment can be used to understand planet formation. Now, in order to do this experiment, you're going to need a few things. You're going to need a fairly large bowl of room temperature water. You're going to need an empty soft drink can. This one's a 200 ml mini can. Doesn't really matter if you use a full size one though. And you're going to need a way to handle hot things safely. You're also going to need a stove. I want you to take the can and place it upside down in the bowl of water and just submerge it. Have a play around and have a feel for what happens. So what you should observe is that the can doesn't crumple, it retains its shape and remains buoyant. Put it in upside down, try it out again, no water comes out, right? No water enters the can through the bottom. So what you're going to do is you're going to want to put a small amount, maybe 10 to 20 mils of water in the bottom of the can, and then you're going to take it over to the stove. Place the can of water on the stove, just set to maximum heat. If you don't have a electric stove, just put a pan on top of the gas stove and place the can on the pan. So now you want to wait until the water starts to boil, which you should be able to hear, and steam starts to rise from the top of the can. Okay, so now our water has started to boil. You can hear it bubbling away and you can see a lot of steam rising from the top of the can. So remember, this will be hot. This. Now just fold it from the bottom and then place it upside down in the water like we did previously. Okay, so that thunk you heard was the can getting crushed. So it's already cooled down. What you'll notice is it is now no longer buoyant, not even a little bit. And if I pull this up, a lot of water is going to come out of this can. Much more than we originally put in that 10 ml. See, the can is crushed. And that is the experiment. Okay, so we've just done our experiment. And if any of you paused the video and were able to predict what would happen when the can of soft drink was placed back into the room temperature water, congratulations. Now we're going to try and explain this experiment. So just to recap the observables from our experiment, the first time when the can was just an empty can, we placed it into the water and it was extremely buoyant. It didn't collapse or crash or anything. Nothing really happened, right? It retained its buoyancy. No water came in through the bottom. We then placed the can with a little bit of water on the bottom onto the stove and then boiled the water. And we waited a little bit as the steam rose through the top of the can. We then took the can and placed it back into the room temperature water, and then the can got crushed. Water entered the bottom of the can and it lost its buoyancy. My question to you now is, try and pause the video and see if you can figure out what's going on here. Why did our can get crushed the second time? Okay, so what's going on here? When we place the can in the water the first time, the can retains its buoyancy and no water enters the can through the bottom. So the reason for this is that the can is full of air. So the air is exerting a pressure on the insides of the walls of the can that is supporting it against the environment, and therefore the can doesn't get crushed and the water can't get in through the bottom. When we boil the water, the liquid water undergoes a phase change into gaseous water, and you see the steam rising from the top of the can. So what this does is, because the temperature of the steam is so hot, it rises to the top of the can and it pushes out the atmospheric air that used to be in the can and replaces it with this water vapor. So when we take the can from the stove and we place it back in the room temperature water, the water vapor, so the steam that's supporting our can against collapse, disappears because it undergoes a phase change back into liquid form, so it condenses. So the support for our can collapses. What we're essentially doing, in fact, is forming a small vacuum inside of our can by doing this. That's sort of how the experiment works, and congratulations if you're able to figure that out. But what does any of this have to do with planet formation? Planets form in a dusty disk around baby stars. So these are stars that haven't yet started fusing hydrogen in their cores, and so they haven't switched on. Once they do switch on, they'll blow away all this dusty disk and planet formation will stop. So the way that planets form is Within this disk, particles of dust collide and they sometimes stick together, forming bigger bits of dust. The bigger bits of dust are slightly larger, which means that they tend to accumulate more efficiently, even more matter, and it's sort of like a runaway effect. The bigger stuff gets bigger and bigger and bigger until eventually you get something roughly planet size or boulder size, and there's an entire hierarchy of these things. Now, the gas in this disk is made up of lots of different stuff, but the three main components are hydrogen, dust, and water. Now, hydrogen gas is by far the most abundant, but it's also extremely light. So what this means is it's very, very difficult for these baby planets as they're forming to hold on to it, right? It tends to escape their influence. Only the most massive with the strongest gravitational fields are able to hold on to their hydrogen gas. Now, in our solar system, only the giant outer planets, Jupiter, Saturn, Uranus, and Neptune, have hydrogen atmospheres today, while the far smaller inner planets, so Mercury, Venus, Earth, and Mars, do not. So they remain rocky and terrestrial, and they do not have hydrogen atmospheres. So this is quite a clear divide, right? Why do gas giants form on the outside and terrestrial planets form on the inside, right? So this is where the phase change of water comes in. So in the dusty disk around baby stars, the temperature changes depending on how far you are away from the star. So hotter temperatures close to the star, colder temperatures further away from the star, as you'd expect. Now, beyond a certain point, the temperature becomes cold enough that water can freeze, right? So it undergoes that phase change from liquid to solid. So this is very important because only solid water can be used when it comes to forming the cores of planets. Liquid water, unless you've got an atmosphere in front of it, will tend to just evaporate away and be lost back into space. So instead of just being able to accumulate the dust in the disk, now you can accumulate the water as well. So this provides a substantial boost to the growth of the planet cores on the outside, what's called the ice line. If you're beyond the ice line and you're able to make use of water, you're able to go much quicker until you reach the critical point where you're massive enough that you can retain hydrogen. And this, at last, gives you access to the most abundant building material available. And your mass grows very, very quickly, able to retain more and more hydrogen until you essentially sweep out in your little vicinity of the disk all the building material available to you. Now, when we do our calculations, we find that, sure enough, the predicted ice line for our solar system lies between Mars and Jupiter. So this does also put Earth in the happy in-between area where liquid water can exist, allowing life and you and me to flourish. So armed with nothing more than the knowledge of the phase change of water, we can actually predict that giant planets should be found in the outer regions of solar system and the rocky planets on the inside. In recent years, our knowledge of planetary systems around other stars has expanded immensely. We've discovered over 4,000 exoplanets, and we have found something surprising. Many of these exoplanets are of a kind completely alien to us. We call them hot Jupiters. So these planets are gas giants that reside extremely close to their host stars, often even inside the orbit of Mercury, the closest planet to our own sun. The picture for planet formation is slightly more complicated than what I've described so far. We now understand that although our own solar system is stable, other solar systems are not. And in fact, we know that in the past, even our own solar system was extremely chaotic. In the early stages of solar system formation, massive planets can migrate in towards their host stars by kicking small planets out of the solar system altogether. I hope you enjoyed this Astronomy in the Home series. If you're interested in learning more about alien planetary systems, check out the website for TESS, a space telescope currently searching for new systems.
Astro 3D is the Australian Research Council's Centre of Excellence for all-sky astrophysics in 3 dimensions. Our astronomers are searching to understand the evolution of the matter, light and elements from the Big Bang to the present day. This Astro in the Home series is your opportunity to unlock the secrets of the universe with your own 2 hands. Find out more by visiting our website, following us on social media, or subscribing to our YouTube channel to be notified whenever we upload new content. Now, go explore the universe.